NASA has announced that its Voyager 1 probe, the most distant human-made object in the universe, is once again sending usable information back to Earth after months of transmitting garbled data. This remarkable achievement comes after 45 incredible years of cruising through the cosmos. Launched in 1977 to explore the outer planets, Voyager 1 has ventured farther than any human-made object in history, and it continues to astonish the world with groundbreaking revelations. Recently, a Nobel Prize-winning scientist revealed that the spacecraft is sending back data that researchers never thought possible. Could this be the key to unlocking the greatest mysteries of deep space? One of the most fascinating aspects of the Voyager missions is how they capitalized on a rare planetary alignment that occurs only once every 176 years. Planets orbit the Sun at different speeds, and in most years, they are not positioned in a way that allows a single spacecraft to visit multiple worlds. However, engineers discovered that in the late 1970s and early 1980s, Jupiter, Saturn, Uranus, and Neptune would align in such a way that a spacecraft could use a series of gravity assists to hop from one planet to the next. This rare opportunity, known as the Grand Tour, was first proposed in NASA's planning circles in the early 1970s. While there were concerns about cost, complexity, and technological limitations, the concept was eventually refined into the two-spacecraft Voyager mission. The alignment was crucial because each gravitational slingshot provided the spacecraft with a free boost in speed, eliminating the need for an impossibly large rocket and massive amounts of fuel. By timing the launches to coincide with this alignment, each Voyager could perform a series of planetary flybys, gather data, and then aim itself at the next target with precision. Although Voyager 2 was launched first on August 20th, 1977, it was Voyager 1, launched on September 5th, 1977, that arrived at Jupiter first due to its faster, shorter trajectory. The decision to name them Voyager 1 and 2 was based on mission objectives rather than launch dates, which sometimes causes confusion. NASA designed Voyager 1 to take a path that would allow it to study Jupiter and Saturn in great detail, particularly Saturn's largest moon, Titan. Meanwhile, Voyager 2 was placed on a slightly slower trajectory, enabling it to continue on to Uranus and Neptune if all went well. This intricate chain of gravity assists required thousands of calculations, careful scheduling, and precise tracking. Teams at NASA's Jet Propulsion Laboratory worked tirelessly to ensure the spacecraft stayed on course, as even a tiny navigational error could have derailed the entire mission. Fortunately, both spacecraft adhered to their paths with remarkable accuracy, thanks in part to NASA's Deep Space Network, which tracked their progress and sent course corrections when needed. The rare planetary alignment allowed NASA to gather a wealth of planetary science in just over a decade. It also set Voyager 1 on a trajectory that would eventually send it soaring out of the plane of the solar system and into interstellar space. For Voyager 2, the alignment enabled it to become the first and only spacecraft to visit Uranus in 1986 and Neptune in 1989. Once the flybys were complete, the alignment had served its purpose, and both spacecraft were flung away from the Sun on escape trajectories. Although the original Grand Tour concept was scaled back from its ambitious multi-probe vision, the two Voyager spacecraft alone achieved one of the most extraordinary feats of exploration in history, made possible by a cosmic coincidence that won't occur again for centuries. The design of the Voyager spacecraft was equally groundbreaking. Built to operate far from the Sun and withstand the harsh conditions of deep space, each Voyager is roughly the size of a small car, featuring a large dish antenna and several instrument booms. These iconic designs have become symbols of space exploration, appearing in documentaries, science features, and even pop culture. One of the biggest challenges was ensuring the spacecraft could survive for years in the cold, radiation-filled depths of space, especially during planetary flybys where gravitational forces and charged particle fields posed significant risks. Each Voyager was equipped with a suite of instruments, including cameras, magnetometers, plasma detectors, and cosmic ray detectors, which captured stunning images and data during their journeys. Over time, some instruments were powered down to conserve energy, but a core set of sensors continues to gather data even today. At the heart of each spacecraft is a main bus housing onboard computers, command systems, fuel tanks, and other critical components. The large high-gain antenna, essential for communication, must remain pointed toward Earth at all times. Given the vast distances involved, signals now take over 20 hours to travel one way, and this delay increases every year. Unlike missions closer to the Sun, the Voyagers rely on radioisotope thermoelectric generators, RTGs, for power. These RTGs use the heat from the decay of plutonium-238 to generate electricity, as solar energy is too weak beyond Jupiter's orbit. While the power output gradually declines, NASA has managed to keep key instruments operational by carefully rationing energy. This innovative power system has allowed the Voyagers to continue functioning in the outer solar system and interstellar space, far beyond their original mission timelines. The Voyagers also feature gyroscopes and thrusters for attitude control, ensuring the dish antenna remains aimed at Earth and allowing for precise instrument adjustments. Communication is facilitated by NASA's Deep Space Network, a global system of antenna stations that has been upgraded over the decades to detect the faint signals from the distant probes. Another iconic feature of the Voyagers is the Golden Record, a 12-inch gold-plated copper disc containing sounds and images selected to represent the diversity of life on Earth. Designed as a cosmic greeting for any potential extraterrestrial intelligence, the record includes spoken greetings in multiple languages, musical pieces from various cultures, and encoded images depicting human society, plants, animals, and the solar system. The robust design of the Voyager spacecraft has been key to their longevity. Built to endure harsh conditions, they feature redundant systems for critical functions such as backup thrusters and computers, which have helped them overcome occasional glitches. Ground controllers have also updated the onboard software over the years, allowing the spacecraft to adapt to new mission phases. This combination of innovative design, meticulous engineering, and careful management has enabled the Voyagers to continue operating decades after their launch, making them enduring symbols of human ingenuity and exploration. A major challenge in designing missions to the outer solar system is powering the spacecraft. While missions closer to Earth can rely on solar panels, the dim sunlight beyond Jupiter makes this impractical. The Voyager's RTGs, which convert the heat from decaying plutonium-238 into electricity, have proven to be a reliable solution. This technology, first used on earlier missions, has allowed the Voyagers to operate in the darkest reaches of space, far beyond the limits of solar power. As the power output slowly declines, NASA has had to make difficult decisions about which instruments to keep active. But the fact that both spacecraft are still communicating with Earth is a testament to the durability and foresight of their design. The Pioneer probes and the Apollo Lunar Surface Experiments packages also utilized RTGs, but their use in the Voyager missions was especially critical. The Voyager spacecraft needed reliability, not just for years, but potentially for decades. At the start of their journey, the RTGs supplied a few hundred watts of power per spacecraft, gradually declining over time. While this might not sound like much, less than a typical household light bulb, it was enough to run the core instruments, telecommunications systems, computers, and heaters that protect the spacecraft from freezing in the harsh environment of space. RTGs are designed with safety in mind. The plutonium-238 is in ceramic form and encapsulated to minimize the risk of scattering radioactive particles in the event of a launch mishap. Fortunately, the Voyager launches were both successful, so these precautions were never put to the test. Once in space, the steady warmth from the radioactive material ensured a stable flow of electricity, which was crucial for capturing images and taking measurements during planetary flybys, as well as powering the spacecraft's internal systems, even when they were operating many astronomical units from the Sun. Over the years, as the plutonium decays and the internal components age, the power output has declined. Mission planners have had to make difficult decisions about which instruments to keep active. By carefully scheduling instrument usage and hibernating certain subsystems, engineers have managed to conserve enough power to keep the Voyagers sending back data. However, eventually the RTGs will not produce enough electricity to run any instruments or keep the antenna properly aimed. Scientists estimate this could happen sometime in the late 2020s or early 2030s, though the exact timeline depends on how the generators degrade and how the spacecraft themselves hold up. Until that day comes, every bit of power is meticulously allocated to extend the spacecraft's life as long as possible. Attitude control systems require small amounts of power to heat the hydrazine fuel lines and keep the thrusters operational. Communication also demands a power. While receiving commands from Earth doesn't consume much energy, transmitting a strong enough signal back to Earth certainly does. Cameras and high-resolution imaging instruments, which required more heated enclosures and greater data bandwidth, had to be powered down over time to save energy. Today, most of the scientific results come from instruments that measure charged particles, cosmic rays, and magnetic fields. Excellent tools for studying interstellar space. Without RTGs, none of this would have been possible. The darkness of the outer solar system offers only a trickle of sunlight, far too weak for standard solar arrays. Any feasible solar solutions from the 1970s would have been enormous, heavy, and likely too fragile to function for decades in such harsh conditions. RTGs, on the other hand, proved to be reliable, compact, and durable, making the Voyager missions a model for how to operate far beyond the inner regions of our planetary neighborhood. Jupiter was the first major destination for both Voyager spacecraft. This massive gas giant, more than 11 times the diameter of Earth, offered a wealth of opportunities to test the spacecraft's instruments and gather new insights about its atmosphere, moons, rings, and intense radiation belts. By the time the Voyagers arrived, scientists predicted that Jupiter would hold many surprises. Pioneer spacecraft had briefly visited in the early 1970s, but their instruments were far more limited. Voyager 1 made its closest approach to Jupiter in March 1979, followed by Voyager 2 in July 1979. One of the most shocking discoveries during these encounters was the intense volcanic activity on Io, one of Jupiter's many moons. Observations revealed multiple active volcanoes spewing sulfur-rich plumes far above Io's surface, stunning scientists who had not expected such geological activity so far from the Sun. This discovery proved that tidal forces from a giant planet could heat and reshape a moon's interior to an extraordinary degree. Another moon, Europa, had fewer visible craters and a smooth, ice-covered surface, hinting at a hidden water ocean beneath its icy crust, an exciting target for future exploration. The Voyagers also brought Jupiter's atmosphere into sharper focus, capturing breathtaking images of the Great Red Spot, a giant storm larger than Earth that has likely raged for centuries. The data revealed swirling cloud patterns, high-speed winds, and lightning in the atmosphere, showing that Jupiter's cloud tops have many layers, with ammonia crystals forming part of the bright, colorful patterns. Additionally, each Voyager found evidence of a faint ring system around Jupiter. Before this, Saturn was known for its rings, but Jupiter's rings had not been clearly identified until the Voyager flybys. Though much dimmer and less extensive than Saturn's, the discovery of Jupiter's rings was another groundbreaking revelation that changed our understanding of the outer planets. Saturn has long been an object of fascination due to its stunning ring system, visible even through low-powered telescopes on Earth. Before the Voyager missions, scientists had only seen Saturn's rings from afar, and while Pioneer 11 had provided some insights, it was nowhere near as detailed as what the Voyagers would achieve. Voyager 1 reached Saturn in late 1980, followed by Voyager 2 in 1981. What the Voyagers discovered at Saturn exceeded all expectations. The spacecraft captured high-resolution images of the rings, revealing that they were composed of countless small particles, ranging from grains of sand to large boulders. Instead of being a few broad, uniform bands, the rings displayed intricate structures, including thin ringlets, gaps, spokes, and waves. This level of detail suggested gravitational interactions between ring particles, small embedded moons, and Saturn's larger moons. Scientists realized that so-called shepherd moons helped maintain the sharp edges of the rings. Another highlight was the close study of Titan, Saturn's largest moon. Titan, which is larger than the planet Mercury, has a substantial atmosphere rich in nitrogen and organic compounds. Unfortunately, the thick haze prevented Voyager 1's visible light cameras from directly observing the surface. However, the data hinted at the possibility of lakes or seas made of methane or ethane, a speculation later confirmed by the Cassini-Huygens mission. Titan quickly became one of the solar system's most intriguing moons, with some scientists considering it a possible analog to early Earth, due to its thick atmosphere and organic chemistry. Saturn's other moons also yielded surprises. Mimas, with its massive Herschel crater, was captured in detail for the first time, giving it a striking resemblance to the Death Star. Enceladus appeared highly reflective, hinting at a bright, icy surface, though its geysers would only be discovered by later missions. The Voyagers also revealed a variety of surface features on moons like Tethys, Dione, and Rhea, contributing to a broader understanding of how icy satellites evolve. During this period, mission controllers faced tough choices. Voyager 1 adjusted its path after Saturn to get a closer look at Titan. which meant it could not continue to Uranus or Neptune. Voyager 2, on the other hand, retained a trajectory that allowed it to visit Uranus and Neptune after Saturn, though it passed Titan at a greater distance. Both spacecraft accomplished their goals at Saturn, capturing transformative data and images that rewrote our understanding of ring physics, moon geology, and the nature of gas giant environments. Voyager 2 holds the distinction of being the only spacecraft ever to visit Uranus and Neptune up close. No other probe has flown by these distant ice giants, making Voyager 2's journey truly unique. When Voyager 2 reached Uranus in January 1986, it revealed a planet unlike anything scientists had imagined. Uranus's pale blue-green atmosphere, tipped on its side due to its extreme axial tilt, was a sight to behold. The spacecraft discovered 10 new moons and 2 new rings, adding to the complexity of the Uranian system. One of the most surprising findings was the planet's lack of internal heat, which contrasted sharply with the other gas giants. Voyager 2 also captured images of Miranda, one of Uranus's moons, revealing a bizarre patchwork surface with cliffs, valleys, and craters that suggested a violent past. This moon's chaotic terrain left scientists puzzled and eager for further exploration. When Voyager 2 arrived at Neptune in August 1989, it uncovered even more astonishing secrets. Neptune's deep blue atmosphere, driven by the fastest winds in the solar system, was a mesmerizing sight. The spacecraft discovered the Great Dark Spot, a massive storm similar to Jupiter's Great Red Spot, though it had vanished by the time the Hubble Space Telescope observed the planet years later. Voyager 2 also revealed 6 new moons and 4 faint rings around Neptune. One of the mission's most thrilling moments was the close flyby of Triton, Neptune's largest moon. Triton's icy surface, dotted with geysers spewing nitrogen gas, suggested active geological processes. The moon's retrograde orbit, moving in the opposite direction of Neptune's rotation, hinted at a captured object from the Kuiper Belt, adding another layer of intrigue to this distant world. Voyager 2's encounters with Uranus and Neptune were nothing short of revolutionary. These flybys provided humanity's first and only close-up views of these enigmatic ice giants, transforming our understanding of their atmospheres, moons, and ring systems. The data collected during these encounters continues to inspire scientists and fuel the desire for future missions to these distant realms. Voyager 2's journey to the outer reaches of the solar system remains one of the most extraordinary achievements in the history of space exploration, a testament to human ingenuity and the relentless pursuit of knowledge. The data gathered by Voyager 2 during its flybys of Uranus and Neptune remain our best direct observations of these distant planets to date. When Voyager 2 arrived at Uranus in January 1986, scientists were both excited and unsure of what to expect. Uranus is a strange and enigmatic planet, primarily due to its extreme axial tilt. Its rotation axis is tipped over by about 98 degrees, making it appear as though it's rolling on its side around the Sun. During the flyby, Voyager 2 revealed that Uranus has a more complex ring system than previously known. Though the rings appeared darker and less extensive than Saturn's, the spacecraft also discovered 10 new moons, adding to the intrigue of this icy giant. One of the most shocking discoveries was the bizarre surface of Miranda, one of Uranus's largest moons. Voyager 2's cameras captured images of canyons, patchwork terrains, and scarps, suggesting a chaotic and violent geological history. Another surprise was Uranus's magnetic field, which does not align with the planet's rotation axis. The field's center is offset from the planet's core, indicating that something unusual is happening deep within Uranus, a mystery that continues to baffle scientists. After its groundbreaking encounter with Uranus, Voyager 2 continued its journey to Neptune, reaching this remote ice giant in August 1989. Neptune's dynamic atmosphere stunned scientists, revealing a great dark spot, reminiscent of Jupiter's great red spot, as well as swiftly moving bright clouds racing at high latitudes. Like Uranus, Neptune also has rings, though they are faint and incomplete. The planet's largest moon, Triton, turned out to be one of the most fascinating discoveries. Triton has a thin nitrogen atmosphere and active geysers spewing nitrogen gas or nitrogen-laden material from its surface. Even more intriguing is Triton's retrograde orbit. It moves in the opposite direction of Neptune's rotation, suggesting it was likely captured by Neptune's gravity at some point in the distant past. Both Uranus and Neptune often receive less attention than Jupiter and Saturn, but Voyager 2's findings proved they are captivating worlds in their own right. The spacecraft's measurements helped researchers refine models of ice giant compositions and raised new questions about how these planets formed. For instance, the presence of water, ammonia, and methane ices in their interiors suggests a different evolutionary path compared to Jupiter and Saturn. The data also hinted at possible ocean layers deep inside these planets, which may influence their unusual magnetic fields. Voyager 2's triumphant flyby of Neptune marked the crowning achievement of its primary mission. After this historic encounter, the spacecraft sped off into the outer reaches of the solar system, having visited 4 outer planets, dozens of moons, and multiple ring systems. Voyager 2 not only fulfilled NASA's hopes, but exceeded them in ways no one could have imagined. Meanwhile, Voyager 1 had already left the plane of the planets after its encounter with Saturn, heading on a trajectory that would eventually carry it into interstellar space. Together, the Voyagers remain enduring symbols of how a well-planned mission can seize a unique orbital opportunity to gather an unprecedented wealth of data. Beyond Neptune, the planets give way to the Kuiper Belt, a zone of small, icy bodies, and even further out lies the hypothetical Oort cloud, a reservoir of comets that may extend nearly halfway to the nearest stars. However, one of the most immediate frontiers after Neptune is the outer boundary of the heliosphere, where the solar wind interacts with the interstellar medium. This boundary is not a single line, but a complex region with multiple zones, including the termination shock, the heliosheath, and the heliopause. The heliosphere is shaped by the solar wind, a stream of charged particles blowing outward from the Sun in all directions. Closer to the Sun, the solar wind flows at supersonic speeds, carrying the Sun's magnetic field lines with it. As it moves farther away, it eventually encounters the interstellar plasma and begins to slow down, forming the termination shock. Beyond this lies the heliosheath, a turbulent region where the solar wind is slowed, compressed, and heated. Finally, there is the heliopause, often described as the boundary between the Sun's domain and interstellar space, though the interaction is far more complex than a simple dividing line. For many years, scientists debated where exactly the heliosphere ends. It was known to extend well beyond the orbit of Pluto, but its exact limits remained a mystery. The Voyagers carried instruments capable of detecting changes in the particle environment and magnetic field as they moved away from the Sun. These readings began to reveal transitions in the flow of charged particles, hinting at the spacecraft's approach to the boundary. However, this boundary is not something that can be photographed. It's detected through changes in the direction of cosmic rays, solar wind speed, and magnetic field patterns. By the late 2000s, data suggested that Voyager 1 had encountered the termination shock, and in 2013, scientists officially announced that it had entered interstellar space based on changes in plasma density readings recorded in 2012. Voyager 2, traveling a different route, crossed into interstellar space in 2014-2018. These transitions were historic moments in space exploration, marking the first time human-made objects had ventured beyond the protective bubble of the solar wind. The discoveries in this boundary zone have already rewritten our understanding of how the Sun interacts with the galaxy. Both spacecraft detected a surprising amount of turbulence, with plasma waves and cosmic rays swirling in ways that were not fully predicted. They also found that the shape of the heliosphere might be more irregular than the neat, comet-like shape proposed by early models. Thanks to these new measurements, scientists are refining their knowledge of the heliosphere's geometry and how it influences cosmic ray penetration into the inner solar system. While we cannot see this boundary in the same way we see a planet or moon, the data on particle flows, plasma density, and magnetic fields tell a fascinating story. They reveal that the solar system is part of a dynamic galactic environment, continually bombarded by high-energy particles from supernovae, pulsars, and countless other cosmic events. The Sun's magnetic field and outflow moderate some of this barrage, though perhaps not as much as once assumed. The termination shock, where the solar wind slows from supersonic to subsonic speeds as it meets the interstellar medium, was a major milestone for both Voyagers. For Voyager 1, this occurred around 94 astronomical units from the Sun, though the exact distance is challenging to pin down due to fluctuations in the shock itself. Voyager 2 reached the termination shock around 84 astronomical units from the Sun, a difference attributed to variations in solar activity and the interstellar